The Euclidean algorithm is a cool algorithm that you can use to find the GCD of really large numbers without having to write out all the factors of each number. Now you might be wondering what GCD means. The GCD of two numbers is the greatest common divisor of the two. The notation reads GCD bracket, then the two numbers close bracket. For example, if you were to write out all the factors of 15 and 30, you'd quickly see that the GCD is 15. How about a different example? The GCD of 130 is 10, as you can see from the list. That's pretty straightforward, but what if the numbers were bigger? What if I told you to find the GCD of 1098 and 2386? We could write out all the factors, but it would take a long time. It's not so easy now, right? The answer is to use an algorithm called the division algorithm. The division algorithm states that any integer a can be written as a product of two other integers, q and b, with remainder r. Using this allows us to rewrite 2386 as a product of 1098 and some other number with some r value. But wait, how does this help us with the GCD problem? We're going to make use of a theorem called GCD with remainders that uses the division algorithm to simplify GCDs. GCD with remainders states that if you have the equation a equals qb plus r, then the GCD of a and b is the GCD of b and r. Repeated use of this algorithm is called the Euclidean algorithm. This will help us simplify the numbers quite a bit. Back to the original example. 2386 can be written as 1098 times 2 with remainder 190. GCD with remainders tells us that the GCD of 2386 and 1098 is equal to the GCD of 1098 and 190. This is a great start, but we can still make it simpler. 1098 becomes our new a value and we keep going. 190 fits into 1098 5 times, and the remainder is 148. That tells us that the GCD of 1098 and 190 is equal to the GCD of 190 and 148. You can really see how numbers are getting smaller and smaller. Then 148 fits into 190 one time, and the remainder is 42. 42 fits into 148 3 times, and the remainder is 22. At this point, we can probably tell that the GCD is going to be 2, but let's do it a few more times just to be sure. 22 fits into 42 one time, and the remainder is 20. 20 fits into 22 one time, leaving a remainder of 2. Finally, 2 fits into 20 exactly 10 times. Once you get to the GCD of some number and 0, you can figure out the GCD from the other number, which is quite convenient. In this case, the GCD is 2. And that's the Euclidean algorithm. Tedious, but of course less tedious than having to write out all the factors of everything for sure. But wait, what if I told you there's another algorithm that's just like this one but like better? That variation allows you to work through the numbers in a table, rather than having to write out equations again and again. This algorithm is called the Extended Euclidean Algorithm, or EEA. To demonstrate this, let's try a different example. Let's say that I wanted to find the GCD of 112 and 768. They're already a bit smaller than the previous example, but it'll still be hard to figure out the GCD just by inspection. So what we do is, we write out the headers for each column, x, y, r, and q. X is the first number, y is the second, r is the remainder, and q is the quotient. Before we begin, I want to introduce the idea of the floor function. The floor of a number is the integer just below that number. For example, the floor of pi is 3, the floor of 7.5 is 7, and the floor of negative 1.141 is negative 2. Basically, for positive numbers, it's just getting rid of decimals. Okay, back to the example. The first two rows that we write are 1, 0, 1, 1, 1, 2, 0, and 0, 1, 7, 6, 8, 0. This is basically saying that 1 times the first number, 1112, has a remainder of 1112, and 1 times the second number has a remainder of 768. Ignore the q values for now. The next row is calculated by taking the floor of 1112 over 768 and putting that as the q value. In this case, the floor is 1. Then, you take the first row and subtract the second row from it, so row 1 minus row 2. This is really row 1 minus 1 times row 2, as you multiply the floor value by row 2 before you subtract. Then you repeat the same process. The next row's Q value is the floor of 768 over 344, which is 2. This time we'll take the second row and subtract the third row, so row 2 minus row 3. But this time the floor value is 2, so you have to multiply row 3 by 2 before subtracting. Just a reminder, this row actually represents the equation negative 2 times 1112 plus 3 times 768 equals 80. So now we just keep going until the R value becomes 0. Now, look at the numbers just above the 0 row. The R value in this row is the GCD of 1112 and 768. And another cool thing is that this row is the solution to the equation 1112s plus 768t is equal to the GCD of 1112 and 768. So if you're also asked to solve the linear equation, s would be negative 29, which is the x value, and t would be 42, which is the y value. And that's the extended Euclidean algorithm. It's pretty useful when dealing with GCDs and also linear equations. Hope you found this video helpful in any way. Let me know if you want to see more videos like this.